one example to show how powerful of the wake flow. So as an example I showing here, the bridge will be broken because the natural frequency of the structures is the same as with the voltage shading frequency. So that's why the bridge will oscillations and then finally broken. Okay, and then the later it is another example as I showing here. Okay, this is airfoil, and then as you can see, there are some eddy flow on the right hand side, and this is right hand eddy flow will also induce instabilities for the airplanes. So finally the airplane will falling down. But the idea is the airfoil need to control some leveling. If the angle is too high, there are some eddy flow in right hand side, and then it is not easy to control the airplane. So finally will falling down. So I just show very quickly some example related to the wake flows. Okay, and usually the wave flows, the starting point we call that is the flow separations. So in that area, the flow will separate and to become the wake flow in right hand side. Another example, this is the flow under the nozzle, and then you can see this is the diameter of the pipe, but there are some cross section area become small. So the idea for this case, because the cross section area decrease, so the flow velocity in here will increase. So the idea is the velocity increase in that area, and then the pressures, the environment pressures will decrease. Okay, I will tell you the reason why the velocity increase and then the pressure decrease. This is based on the Bernoulli equations ideas, but I didn't teach before, so you don't understand the reason why. But in here, if the velocity increase and pressure decrease, if the pressure is lower than vapor pressures, and then the water flow will become the air bubble. As I mentioned before, the air bubble will cause the cavitation phenomena. And then in another case, you can see here, there are eddy flow around the pipe boundaries. And then the eddy flow will also destroy the pipe wall in here. Okay, so I put the photos related to the cavitation problems. As I mentioned, the air bubble will make some erosions of the infrastructures, like this is the spillway. The spillway, as you can see, there are some structures will be destroyed by the air bubbles, and some fans also be broken. Okay, so for the design, the idea is the environment pressure cannot lower than vapor pressure. Okay, so the vapor pressure is the liquid and the air boundaries, the phase boundary. Okay, the vapor pressure, if your environment pressure is lower than vapor pressure, the liquid will become the air bubbles, and the air bubble is very powerful. It's very powerful to destroy some infrastructure service. So for engineering designers, they need to design. Because we know the velocity increase and the vapor environment pressure decrease, So for the idea, we cannot have very higher speed of the flow water, right? So we need to control the speed of the flow water. If the water speed is higher than some criteria, the pressure will become lower and lower than vapor pressure, and you will get some trouble. So the idea is we need to control the velocity first, and then we can avoid some terrible phenomena like the photo showing here. Okay, so but the idea is here, the key knowledge. So this chapter will tell you why the velocity increase and then pressure decrease. Okay, so I will tell you the answer, the reason why. So in our laboratory experiments next semesters, as you can see here, this is a very easy laboratory experiment because we just observe some stream flow. As you see here, if I put some particle in here, and then we can control the flow velocities inside our systems, and we can observe how changes of the stream lines. Okay, so the idea is we know laminar flow and the turbulent flow, the significant difference is the velocity speed. If we can change the velocity speed to low and high, and then you can have the different conditions for the laminar flow and the turbulent flows. As I define the Reynolds numbers is equal to the ratios. The lower is mu, is the viscosity parameters, and the upper is the rho and the velocity of the water flow and the diameters of the pipe. So in our laboratory experiment, we already control the diameters, and we control our fluid is waters. And as we know, the water, we can also fix the dynamic viscosity. So only one parameter is velocities that we can control different velocities. Okay, and then the second idea is not only use the circle panels, we can change the different panel shape and redo experiment again and observe how changes of the stream lines. So it's quite easy experiment in next semesters, and as you can see, there are some. This is the flow separation point, and then after that, there are some AD flow will come inside in here. But before that, there is no AD flow in front of the particles. So we are trying to conduct the laboratory experiment to observe such kind of the phenomena as we teach in class. Okay, so we move to the next. Because this chapter, our topic focuses on kinematic properties, and as I mentioned, the first one important is velocity, and the second one is accelerations. So right now we are focused on the acceleration problems. So two reasons why we need to know accelerations. The first, predicting force is important to engineer designers. And the second, usually the forces are related to the accelerations. So we need to define the acceleration first, and then we can understand what the force contributed from accelerations. So this is the flow. And as you see the flow in these directions, but if the flow particle is close to the bubble, the ball here, and then the velocity will trying to decrease now. So your acceleration direction is opposite directions because the velocity is decreased along these directions. So let's just try to emphasize again, the acceleration directions usually depend on the velocity field changes patterns. Okay, it's a quite simple idea. So basically, we have two components of the acceleration. The first one is a normal component. The second one is the tangent components. So we are familiar with if there are some centripetal accelerations. So you know usually this acceleration usually try to change the direction of the flow velocities. But the tangent components acceleration usually change the speed of the velocities. So you have two kind of acceleration. The first one, normal, is try to change the directions. The second is a tangent acceleration, is try to change the speed. Okay, so before we discuss some force contributed from acceleration, we need to know two kind of acceleration here. First one is normal, the second is the tangents. Okay, so as you see, finally we can summarize the acceleration to become the following properties here. But so we start from, we define the velocity as function of the string line. This is S is string line space, and as function of the time. Okay, and this velocity with the factors is along the tangent directions. It's along the tangent direction. So this is our string line. And if I discuss this point, and what are the velocity? The velocity we discuss with the tangent velocities. So this is the V, S, T at the different string line locations at the different time point, and the direction is along the tangent directions. This is the unit factors of the tangent directions. So, and then we can define this is the factors velocities. Okay, so we know actually the velocity is equal to the acceleration is equal to the velocity with the time differentials. So we start from the dv factors and the dt, and we know the v factors can replaced by the v as function of the string line location and the different time point, and with the directions along the tangent directions. So if you do the differential with the time, so we have the dt and vst, and this is the unit factors we take outside. Is ut, the unit factors along the tangent directions. And the second item is we don't do the differential with the velocity. We only do the differential with the ut. So we keep the vst outside, and the unit factor t tangents with the time changes. Okay, so we have the two items differential. The first item is we try to do the differential computing with the velocity field, and the second we do the differential for the unit tangent factors. Okay, so this is our first items, and this is the second items we trying to understand. So the first one, the t, and we do the s and t function of the velocities for the velocities. So we can decomposed to the partial streamline differentials. So we have partial streamline differentials and streamline change with the different timings differential. And you take a look, the ds differential s can cancel out, and then back to the dv over dt. Okay, and the second item is plus. We do exactly the partial t with the v as just simply the partial v partial t, right? dv dt. Okay, so for here you know the streamline location change with the time is equal to velocity. This item is equal to the velocity. So the first part in here we can rewrite to v dv ds multiply v, because ds dt is equal to velocity. And the right hand side dv dt, we just keep it. Okay, so this is a final formula for our first items. But here, the much difficult to understand is the second item too here. What is the dut unit vectors dt? That means the unit vector along the tangent direction change with the time. So what it is? Okay, so I plot the figure here. This is our streamline, and maybe this is the point. This is a point, and we have the ut unit vectors at the time point along these directions. Okay, this is a unit vector along the tangent directions at the time point t. And we may have several seconds later, and we have this point, and the tangent direction is here along these directions. And this is a ut and plus the delta t, because the delta t later, and you can see the changes, the direction changes of the unit tangent vectors. Okay, so the idea is, if I plot, and we can select one point like here, and this is our centers of the curvature center here, and the line, this is the line, and this is the line. And we can say this line vectors are vectors at the time point. And this is are vectors at the time plus delta t. Okay, and we see the changes angle here, we can say that is d theta. It is the angle changed. This is the angle changed. Okay, so if I plot, this is this is the ut unit vectors at the time t time point, and this is the ut unit vectors at the t plus delta t. And you know the changes. What the changes? The changes here d you can say the delta t unit vector changes is equal to the ut bar t plus delta t minus ut bar t, right? It's the delta changes. For the vector changes, we know the directions is along here, right? This direction is the delta unit vector t. This is the directions. And how about the length of the delta ut unit vectors? What is the length? What is the length? As you see, this is, we know the angle d theta here, and that means the angle here also the d theta. And if we can know the length here, the length L here, so the absolute delta ut length is equal to L multiply the d theta. D theta here, and we have the L length. So the absolute length of the delta ut vectors is L multiply d theta. And then you see here, what is L? Because we are talking about the unit vectors. So the length here is equal to 1. Because the vector is unit vector, so the length of the unit vector is 1. Okay, so actually the answer in here is d theta. The length of the delta ut vector is d theta. Okay, so you know the angle, the arrow direction showing here, I can tell you the direction is along the u normal directions. Because if two tangent unit vectors are quite close, that means the delta t is very small. And then this angle direction, this arrow directions is downward of the curvatures. So in these directions, we call that is the normal directions. Okay, so we know the differential of the unit vector, the direction will change to the normal directions. And the amplitudes, the length of the vector is d theta in here. And the d theta have the delta t time changes. So here is dt. So if you can understand the unit vector along the tangent directions change with the time is equal to the d theta divided dt, and the vector changes to the normal directions. And then we know this item is angle velocity. D theta dt is omega, right? It's angular velocities, and with the normal directions. And we also know the angular velocity is equal to the velocity divided the radius. And so we rewrite to here to be the v divided v. So in here. Okay, so right now we try to find the answer for the item 1 and the item 2. The item 1, the answer shown here. And we summarize in here. Okay, and the item 2 is finally equal to v divided r, and the direction change to the normal. And we need to multiply v again. So that's why the final acceleration term is v squared divided r. Okay, so usually we have the 3 accelerations. So the first one we call that is convective acceleration. The second one is the local acceleration. The final one is centripetal accelerations. Okay, and the first 2 items we call that the direction is tangent directions, and the final one is the normal directions. So you need to keep in mind, if you have the velocity field, and can you compute the acceleration with the different components? The first component is tangent component, and the tangent component includes 2 items. One is related to the spatial. Another is related to the time domains. So you have two domains. First is spatial domain. The second is time domains. But they are contribute along the tangent directions. And the final item is different directions is normal components. And the normal components, we will compute the acceleration based on v squared divided radius. Okay? So you need to keep it in mind. So we have the problems. So this is an exercise. If I provide the velocity field, as you see, this velocity field is along the x directions, and they say we have the u0, and the u0 is entrance velocity is equal to 10 meters per second. So we have a u0, the entrance velocity is 10 meters per second. And the question tells you the length along the directions, x directions L, is equal to 0.5 meters. And the question tells you the velocity is uniform flow. You see here, the velocity is uniform flow. So all of the straight line is parallel each others along the x direction. So that's a straight line like this showing here. And each velocity field at this profile is the same velocity speed. Okay, because the uniform flow, so there is no any curvatures. If it's not the curvature flow, so we don't have the acceleration along the normal components, because the flow is linear flow. It's not the curvature flow. If the curvature flow, we have the normal components acceleration, because the direction changes, the flow direction changes, and if we have the flow accelerations along the normal direction, but if we don't have, so the flow is linear. And if you go back to see our questions, it's a uniform flow and the linear direction along the x. So we don't have the acceleration patterns for the normal component. So you see the answer for the normal component of acceleration is equal to 0. So in our question, we only have the acceleration along the x. So we rewrite the equation showing here. We are discussed for the direction along the x. So we use the ax is equal to v, and we can change the v to u, because I tell you for the x component velocity we use the u parameters. So we know that the u follow these equations, and the s here, our s direction is parallel to x. So in here I use the dx, and the plus du dt. Okay, so you take a look, the u function defined here, and there are no parameters related to time. That means this is a steady flow. If the steady flow, so we don't have the item for this part. And these items, we call that is a local acceleration is equal to 0. Because the u functions, there is no t. Okay, only velocity as function of the x, no t parameters. So we just focus on these items. So following the question, you see, find the accelerations at the station halfway. That means the question would like to you answer the point in here is half location in here. What is the acceleration at this point? What is the acceleration at this point? And you can say halfway position is x divided L is equal to 0.5. Okay, so first we need to solve u. What is u at the x equal to 2 over L? And then you know the L. What is the L? L in here is 0.5. And you know the function defined here. Okay, so we have the u0 divided 1 minus 0.5. What is the x? X divided L is equal to 0.5. X divided L is equal to 0.5. So here I can use the 0.5. And what is u0 is the 10. u0 is the 10. So the idea is here is 10 divided 1 minus 0.25. Okay, so you know the answers. I forgot to bring my calculators. So wait. So can you tell me the answer for this? It's 10 divided the 0.75. So around the 13.33. Okay, the meters per second. And then the second we need to find out the differentials, the u du dt dx. So we take the constant outside. u0 is a constant, and dx, and the inside is the 1 minus 0.5 x divided L, and I use the minus 1 here. And I will try to do the differential for these items. So the result is u0 and the minus 1 and 1 minus 0.5 x divided L, and become the minus 2. And here is still the x function, so we need to partial differential of the x. So after that you have the minus 0.5, and here is L divided L. Okay, so you can summarize the following equation here. So the constant u0 here is minus 1, and there is a minus, so become the positive. So 0.5 divided L, and the right hand side is 1 minus 0.5 x L minus 2. Okay, so you just put the x is equal to 0.5 L, and then you know here L is 0.5. So your x is equal to 0.25. Okay, so you just put the x inside, and you know the L is 0.5, and you can compute the differential du and the dx solutions. So I just put a number inside. This is 10. u0 is 10, and multiply the 0.5, and L is also the 0.5. So this is equal to 1. And the right hand side is 1 minus 0.5 multiply 0.5. X divided L is 0.5 here, and minus 2. Okay, so you can compute by yourself. So It is the 10 divided the 0.75 square. Okay, so 0.75 multiply 0.75 and 10 divided it. Around the 17.78. Okay, so and then you put back in here. So you exactly know the AAX is 13.33 multiply 78.78, and you have the answer around these numbers. Okay, 237 meter per second square. Okay, so the question is very simple ideas. If you have the velocity field, and then you can compute any accelerations from the velocity field, and some velocity not only as function of the x, maybe as function of the timing. So if the velocity change with the time, that means the flow is unsteady flow. So you need to double check what kind of flow you have, and then you can try to find the answers. Okay, so the second problem is focus on the nozzle, and this is a nozzle with the diameter d, and the question tell you the flow velocity is linearly from the base is here to the tips in here is linearly changed. Okay, so and assume this flow is one-dimensional flow. So what is the convective accelerations at the midway between the base and the tip? Okay, so I correct is the base should be the question tell you the base is located here. So that's why they provide the arrow in here. So here is the base, and here is the tip. Oh, but the arrow in here, so here is the tip. Okay, so the question just directly tell you you need to answer the question for the convective accelerations. So as we remember, the convective acceleration is equal to v dv ds, right? So we just focus on these items, and then but the question only tell you the velocity in here is 1 feet per second, and in here is the 6 ft per second. So, but you need to answer the questions for convective acceleration in here. So the first one, you need to know the velocity in here, right? What is the velocity in here? Because you just focus on the midway. So you just focus on the point in here, and then we need to know the gradients of the velocity. So, but we only have the 1 foot per second and the 6 foot per second here. So we can compute the dv dx. This is along the x directions. Okay, so very quickly we have the velocity in here 6, and we have the velocity here is 1, and the x distance changes is L. And what is the L? Okay, the L showing here. That the question tell you the answer for the L is 25 inch. So you need to change the inch to ft, right? So how to change? The 12 inch equal to 1 ft. So here is 12, 25 divided 12. So you exactly know how the length in ft unit. So 25 divided 12 is equal to 2.083. Okay, and this is the foot unit. And so here we need to divide the L, the distance along these directions. So here is a 2.083. Okay, so 5 divided 2.083 is around the 2.4. Around the 2.4. Okay, so this is the gradient of the spatial. So the unit is second over 1. It is a second over 1. This is the unit. The unit. And what is the u at these directions, at this point? So we know the distance in here is L divided 2. And we know the starting point of the velocity is 1. So we have the 1 ft divided seconds plus, this is our gradient, dv dx, multiply the location length here, 2 over L. 2 over L. So here is the 1 plus, and the gradient of the velocity along spatial is 2.4. And this is 2, and the length is 2.083. So you can compute the answers. Okay, so 2.4 multiply 2.083 and divided 2. Okay, and multiply 1. The answer is not correct. This is a 5 changes with the length 2.4. Oh, sorry. So here we just compute the answer for the flow velocity at the midway, right? So here is 2.499. It's ft per seconds. So our final answer is following these equations. So we need to compute the accelerations for the convective, and the v is u in here, around the 2.5, and the velocity gradient du ds is around the 2.4 here. So we can just multiply the around the 2.5, multiply the 2.4, and the answer is accelerations. Okay. But still, oh, this here is a +1, right? So here's a +1, so it's a +1, so it becomes a 3.5. Okay, we calculate the 3.5 multiply 2.4. It's around the 8.4 foot per second square. Okay, so the question is quite simple ideas. You just take a look at the velocity functions. If we don't have the velocity functions, and the question will tell you some boundary conditions, like this problem. If we have the starting point velocity and the velocity in the end, and we can compute the gradient by ourselves, and we still can try to answer what is the convective accelerations. Okay, so for the acceleration, we only show two examples here, and you see you need to remember we have the three accelerations. The first one is here, convective acceleration. The second one is local acceleration. It's related to dv dt. Okay, dv dt is a local acceleration. And the final one is the acceleration along the normal component. We call that is the centripetal accelerations, and defined it by the v squared divided radius r. Okay, so totally we only have the three acceleration and with different components, tangent and the normal. That's all. So you need to remember if you have the velocity, and then you can compute the acceleration by yourself. Okay, so we start here, and we have a 10 minutes break. And after we back, I will teach you the Euler equations. Okay?